need to make sure that the beam is able to resist this deflection. We've already done all the calculations up to this point. We've calculated the allowable deflection for the live load and the dead load, and then the case where it's just the live load. So let's go ahead and look at the case where it's the live load and the dead load. And going back to the first video, this was 1,000 pounds per lineal foot. Is the dead load and live load put together. So the next step, or the last few, the thing that we're going to do next is calculate. It's called delta max. And so this is the maximum deflection of that beam. And for a equally distributed or a distributed load on here, the formula is 5WL divided by 384 times the modulus of elasticity time of the steel, and then times the moment of inertia for the beam. So this formula is kind of interesting. We have on the top in the numerator we have 5WL. The W is the weight of the beam per foot, and so that goes here. The L is the length of the beam. So on top I have, oops, and I forgot one other little piece of this formula that would have really messed us up in the end. So I'm glad I just saw that. This WL raised to the 4th power. The L is the length of the beam. And we're going to have to convert a lot of things in this formula. Because out on the delta max, this comes out in inches. And we're going to put in here feet, we're going to put in here pounds, and we're going to put in here PSI, and inches raised to the 4th power, and all that has to come out in 1 unit of inches. So there's a lot of conversions that are going to happen. But on top, we have what's going to cause the bending divided by what's going to be the resisting the bending. Okay? So E is the modulus of elasticity for steel. That is the resistance of the material to bending, whereas the I is the resistance of the shape of that material to bending. So those two numbers are going to cause us to get an answer of how much of this is going to deflect. So this is going to be pretty entailed in doing the conversions. But our delta max is equal to 5 and times 1,000 pounds per foot. And I need to make sure that I get, first of all, 1,000 in there. But I need to convert this into inches, or pounds per inches. And so I'm going to divide 1,000, so it's going to be 1 foot divided by 12 inches. And this is where my feet are going to cancel out, and I'm going to be pounds per inch. And then I need to convert the length of this beam, which once again was 18 feet, into inches. So I've got to do 12 inches divided by 1 foot. And the feet cancel out, and I'm left with inches. And it's a good thing that the top requires so much room, because underneath we have some really, really big numbers. We have the 384, and the modulus of elasticity for steel is 29 million. All right. So that is the resistance of the steel to bending. Then I've got the I value, which I have to look up, which is the resistance of that W12 by 14 beam. So we're going to go back to that structuraldraftingnet.com and look up the moment of inertia for the beam that we were looking for, that W12 by 14. So let's look at that table. The table is over here, and the column that we are going to be paying attention to is this one right here. And so we're looking up our W12 by 14, going across here, and finding that my moment of inertia in the x-axis, or the resistance to bending due to the shape, is 88.6, and this is inches to the 4th power. And so that's an interesting unit that we're going to look at. We have a lot of canceling out to do as we go through this formula. So I'm going to come back over to my formula and put in 88. You know what, let me put my units in over here like I've been meaning to do. I was always really bad about putting the units in the formulas when I was in class, and now I have to make sure I get all my units in here again. So that's 22 million pounds per square inch times the I value, or my moment of inertia, 88.6 inches to the fourth. And I forgot, once again, out of my formula that those feet, the length of the beam needs to be raised to the fourth power. So let's go ahead and work that through on our calculator and get the amounts that's going on there. So let's cancel out a couple of units. So I've got pounds that are going to cancel out here, pounds up here that are going to cancel out. I've got an inch that's going to end up on the numerator. I'm going to cancel one of these. And then when I take this, raise it to the fourth power here, that's going to be inches to the fourth. So that's going to cancel, and that's going to cancel. Don't forget, though, that you still need to raise 216 raised to the fourth power up here. I know I've had a couple of students forget that because I showed that it canceled out here. So it cancels out the inches to the fourth power, but it does not cancel out the number, so don't forget to do that. So the delta max that we're looking for, or that this beam's actually going to have, is equal to, so once we figure all this out, it's 0.919 inches. And back from our previous video where we calculated the allowable deflection, this does not work. So it had to be less than or equal to 0.9 inches, which this does not meet that requirement. So this beam that we've been working on for so long doesn't meet the requirement for deflection. It meets every other requirement, but does not meet this deflection requirement. And so, right away, you want to just throw your hands up and say, "This is just too much work to come to this point and find out it doesn't work." Luckily, we're just going to go with a bigger beam. This beam, this W10 or W12 by 14, works up until this point. So if I go with a larger beam, I'm not going to change any of those other values. And as long as I go with a larger I value for the beam, it's going to do the job. So let's go find a beam with a larger I value. We'll go up to the next step, and we'll try that one to see what we get. So the W12 by 14 here does not work. And so we go up to the next one, which is this W12 by 16, right here. And its moment of inertia is 103. So we'll go back to our formula. We're going to rerun this entire formula, but instead of doing this 88.6, we're going to do 103. And the answer for that, so this is for the W12 by 14. Let's figure out what the answer is for the W12 by 16. I'll run that through the calculator and come up with an answer. And we'll double check to see what our new value is. And the new value with this new beam is 0.79 inches. And so 0.79 inches is less than or equal to 0.9 inches, which was our deflection for the live load and the dead load. So my W12 by 16 works. And since we didn't go smaller, all those other numbers are going to still be larger than what we came up with, because all the other equations are just going to work out. So the W12 by 16 so far works out for the live load and dead load deflection. But don't forget, we have to do this again for just the live load. And so I'll go to another couple slides here, and we'll do the deflection for just the live load. And so the formula is the same. W5, WL, raised to the fourth, divided by 384 times 29 million times E, or times E times I, which is going to be 103 this time. The difference is going to be our W. So let's go ahead and do that. The weight of the beam per foot is going to be the live load, which is 100 pounds per square foot, times the tributary width, and tributary width was 6.66. And so the W in the case of just the live load is going to be 666.66 pounds per foot. Okay? So this is the W that we're going to use this time instead of that 1,000. So we put all these numbers in again. We have 5 times 666.66. And this is in pounds per foot. And I got to get this in inches. So I've got 1 foot times 1 foot divided by 12 inches causes the feet to cancel out, times, we're just going to do the length of the beam as 216, because we already know the length of the beam did not change, and once again that's raised to the 4th power. Alright, divided by 384 times 29 million times 103 is going to get us our deflection for the live load. So that's our delta max again. So let's run that and figure out what we got. So after running all of that, my delta max for just the live load is equal to 0.527. And our deflection limit for the live load alone was 0.6. So my 0.527 inches deflection is less than or equal to 0.6 inches. And so this W12 by 16, right? W12 by 16 beam works. And that is how you do a design.